Hello, PreCalc. I'm going to quickly run through the first operation in our new topic for matrices. And first of all, I want to define a matrix. You've had this before, so I'm going to move through it quickly. You can stop the video if you need, if I'm going too quickly. Pause it, get the information down, come back to us. A matrix is defined as a rectangular array of numbers. Here's an example of a matrix. Notice it's in those bracketed box, that's a bracketed box, that is typical of a matrix. The order of the matrix is its size. So this one is a 2 by 3. We always do the rows, the number of rows, 1 row, 2 rows, and the number of columns. 1 column, 2 columns, 3 columns. The order of this matrix is a 2 by 3. I'm going to teach you how to take a matrix, or not a matrix, a system of equations. Here we have 3 equations and 3 unknowns. X, Y, and Z are the unknowns, and I want you to solve them, solve for those variables X, Y, and Z using matrix operations. So first of all, you're going to change the problem to what's called an augmented matrix. An augmented matrix will pick up the coefficients only of each of these terms and the coefficients and the constants, and we'll put them in matrix form. So here is the augmented matrix. So I took the 1, the -4, the 3, and the 5, and it became the first row in my augmented matrix. Notice the -1, 3, and -1, -3 became the second row, and the third will be a 2. This Y term is missing. As you might suspect, I'm going to hold that place, with a 0 in my matrix, -4 and 6. That creates the augmented matrix. Go ahead and divide the variables from the constants with a vertical dotted line, and you're ready to go. In order to solve for X, Y, and Z, there are certain operations that are allowed in matrix land. So the elementary row operations must be written down. And here they are. Number 1, you may exchange rows. Row number 1 and 3 can, in other words, be exchanged. Row 3 can become row 1, and row 1 can become row 3. Or you can exchange any 2 rows. You can, number 2, the other operation, you can multiply an entire row by a constant. And number 3, you can multiply a row by a constant and add those numbers to another row, replacing the latter row. Right, jot down those rules and come back to see how we're going to continue to solve this for X, Y, and Z. Our goal in finding X, Y, and Z, on our very last step, we want to have a matrix that looks like this. Notice there is a diagonal of 1s. So there's a 1 here, here, and here. Notice under the diagonal are all zeros, and above are numbers. So when we're at this point, we can solve the matrix. We can solve the system. So we want it to get to that point tonight. There are other ways to do this, but we're going to work it out this way. All right. From doing substitution and elimination, I found the answer to this problem is a ordered triplet where X is 7, Y is 2, and Z is 2. Now I'm going to show you how to get that out of the matrix. I'm going to take the augmented matrix that I established in a previous step. I'm going to take and do one of the elementary row operations. what I want to do is begin to establish the zeros and the ones. So I'm going to try, I see there's already a 1 in my first, there's already a 1 there. Sorry. So I want this to be a 0 and this to be a 0. It is a 2. So what can I do? What row operation can I do in order to change that? I'm going to use the third row operation. I'm going to multiply row 1 by -2 and add it to row 3. That's the only way, using the elementary row operations, that I can change that 2 to the 0. Notice how I wrote that. -2 times all the elements in row 1, add it to row 3. Here's what it'll look like. I'm going to take -2 times this value, add it to this. That will get the desired 0. But I have to do that here as well, here as well, and here as well. So -2 times this gives me an 8. Add it to this gives me an 8. Notice the 8 in that position. -2 times 3 gives me a -6. Add it to -4 gives me a -10 in that position. -2 times 5 gives me -10. Add it to 6 gives me a -4. Notice the first and second rows do not change at all. Only the third. Alright, so this looks hunky-dory. Now I want this to be a 0, a 1, and a 0. Or I'm sorry, any number, a 1, and a 0. So I'm working on getting my diagonals. So what row operation can change this to a 1? The row operation is you can multiply everything in a row by a certain number. So I'm going to do that. I'm going to take row 2 and divide it by -1. When you divide or multiply, same difference. So you can divide or multiply everything in the row by a given number. I chose -1 because I'm trying to change that to a 1. I must do it to everything in the row. This row is unaffected. This row is unaffected. Write them in the next matrix unchanged. Now write everything in this row multiplied by -1. Did you get this matrix? Alright, everything, this times -1, this times -1, this times -1, and this times -1. Alright, now we've got the 1, 1, and now I need this to be a 0, so I'm going to eyeball that. If you go in this order, doing your 1s and then the 0s below those 1s, you will never get confused. Alright, so what can I do to change that 8? I can't subtract 7 from everything. That's not one of the row operations. What I can use this row and multiply it by something and add it to this row, where this row changes and these two stay the same. So I'm going to multiply this by what to add it to this to get a 0? Obviously, -8. -8 times row 2 plus row 3. That will change row 3 only. When I multiply this by -8 and add it to this, I get 0. And I multiply this by -8, it becomes 16. Add it to this, becomes 16 minus 10, or 6. And lastly, when I multiply this by -8, I get 16 minus 4 is 12. Alright, we're almost done. So, I wanted a diagonal of 1s and 0s below, so I'm up to here. What row operation will get this to be a 6? I can divide or multiply everything by a number, so I'm going to take row 3 and divide everything by 6. Alright, so we divide everything by 6. The last row is changed only. It becomes 0, 0, 1, 2. And now we are in the form we were trying to get. The diagonals, 1 in diagonals, and 0s below those 1s. Alright, now I'm going to take this information and put it back into equation form. So this is my coefficient for x, coefficient for y, coefficient for z, and my constant equals my constant. Alright, so changing all that back, we get this. Notice the very last statement is the most powerful, where we get no x's, no y's, and we get z equals 2. And that will always happen in the last row and in this size problem. So z equals 2. So I can back substitute that into this equation where y minus 2z equals minus 2. When I put the 2 into this equation for z, I can solve that for y. And then I can put that answer, all those answers, back in the original to get x. So when I did it over here, when I put 2 in for z here, I got that y equals 2. And then I back substitute it into the last one, y equals 2, z equals 2, and I solved that for x, and x came up to be 7. 7 for x, y is 2, and z is 2. We write that as an ordered triplet. We knew that was the answer. Now we can do it with matrices. So why do it the hard way, the long way, when you have substitution and elimination that you could have done from the beginning? It is because this has computer applications. We can't get a computer to think through elimination and substitution, but these rhythmic steps a computer can do. It can be programmed to do those. So we can take very complex problems and feed them into a machine. So anyone who has any future in computers, matrices will be part of that, I promise. All right, let us keep these processes on hold for our work after our test or quiz on conic sections and polar graphing. Till then, have a good evening.